So we went over this probabilistic or Bayesian filter. And I should say, the last thing I was emphasizing was that in the case of continuous spaces, or even for very large discrete spaces, these integrals can get quite complicated, right? And if you imagine, try to imagine these gigantic state spaces that we talked about earlier in the course, like a state space over all possible environments, right? Would you want to integrate over that? Right? Even putting probability measure over that is kind of complicated, I would say, right? What would a prior look like on the space of all polygons, on the space of all simple polygons, right? That would be a very difficult thing to try to formulate. So, so things get difficult very quickly. One of the things people do in robotics that's been very, very successful is to develop particle filters. So the idea for that, since it's impossible to efficiently compute these posteriors or Bayesian updates over the state space, people develop sampling-based methods. The idea is you carry around a collection of samples, say S sub k. I'll show a picture of this in a minute, but I just want to kind of give the steps here. You carry around this collection of samples, S sub k. These are sampled in some way. They're approximately representing this distribution, P sub k. And by P sub k, I just mean probably what I've called my P sub k here. I just mean P of x of k, a to k. So suppose it's that. Be my P sub k here. Just write it in shorthand. And then I want to generate a new sample for sk plus 1 for the next step. And the way I do that is I generate each sample according to this density here, which is pxk plus 1 given xk uk. And then we assign some weight to the sample. These samples have weights associated with them in addition, and that uses the sensing model for that. So that's p of yk plus 1 given xk plus 1. I don't have the proofs with me that, and I don't want to argue the proofs that this is that this will actually provide a reasonable representation or approximation of the probability distribution. I just want to say that you can use the two model pieces here and a collection of samples and keep iterating to provide some kind of sampling-based approach. Just like when you want to do integration, people do Monte Carlo integration of complicated functions very often. So that's the same kind of idea here. Particle filters have been around in statistics literature for many, many years. But they became very, very popular in robotics, I'd say starting about 15 years or so ago. So for example, for a localization problem, this is borrowed some work from my colleagues here. You have a robot in some complicated indoor environment, and it has sonars. So the blue lines are showing what the sonars are reading, and it's very noisy data. It's showing the directions of those. And the red dots represent the possible places for the robot. So that's a collection of particles. And then as the robot moves around, they show that the particles tend to gather. This is corresponding to a distribution that is less uniform than this one, right? Has lower entropy, if you like, if you know that about distributions or densities. And then we go even further. I tried keeping going. and then we go further, and now you see there's a couple of possibilities here. The reason why this seems to happen is because there's symmetry here, right? There's a rectangular room here, and the robot might be this way or this way, right? It could be in either location. This way maybe facing down, this way facing up. It would look about the same, right? And then eventually after it moves in here, it gets enough information to distinguish exactly where it's at. So people compute these Bayesian filters in terms of sampling-based approximations using particles. So what I want to say is that that's led to a huge amount of research, a very active community for many years. They continue to do some of these kinds of things. And even without localization, when we get to the bigger problem, I should say, of localization and mapping at the same time, they tend to do the same thing. So they develop particle filters on the space of environments. They don't define it as a space of polygons as we do, but they rather talk about an environment as a collection of points, much like you would get from range data. And then they build filters over these with the particle filter approximation, let's say, a sampling-based approach. So all of the computational difficulty for them is just to compute this filter. I propose trying to make very simple filters that are very easy to compute and then build interesting planning algorithms on top of them. So that's, in some sense, that's the idea. So the Bayesian approaches get so complex that even to just compute these sampling-based approximations of the filter, it works reasonably well, but it's quite challenging. And in many cases, it's hard to provide theoretical guarantees that it converges. Or maybe there's a theoretical guarantee that it converges, but there's not one that converges to the actual solution, the actual optimum. So there's a difference between converging and converging to the answer, right? So it may converge prematurely, let's say. So there's very, very much difficulty in these kinds of methods. They have worked well in practice, but the theory in some sense is far behind on that, I think. And I want to consider the possibility of making much, much weaker sensors, ones that, like these non-deterministic ones, might have hopefully some easier computations. And we can even put probabilities on top of those. So instead of sampling, here's a way to look at it, and this may be appealing to a group who likes computational geometry. Instead of sampling, let's think combinatorially to reduce the complexity. And then put probabilities back in again to handle noise and things like that. That's going to be the idea. Rather than immediately going to probabilities, making enormous Bayesian posteriors to compute, and then having to only do things in a sampling-based way, because you have no choice at that point. I should point out, there's one very special kind of Bayesian filter for which you do not have to do this kind of calculations, these kind of sampling-based ones. Has anyone heard of the Kalman filter? Who's heard of that? Right. That's right. Has anyone in Professor Mohada's group heard of the Kalman filter? Heard of? Okay, you've heard of it, but not using it. Probably, the reason why I'm asking is that the people who came here from other groups, especially the robotics students, all know it like it's, their common thing. But, computational geometers don't have much to do with it. It doesn't do much for them, right? It's very big in control theory. And I just want to point out that it's a special case of Bayesian filters where something beautiful happens. The complexity gets reduced for a certain reason, which I'll show you. And I'm going to give you some other examples where the complexity gets reduced for combinatorial reasons. But the Kalman filter is interesting to study because I just thought it was very nice. For this particular case, which is very popular in control theorists love linear systems. Anybody know why? Because you can solve for everything you want in linear algebra. And then when you get to nonlinear algebra, or whatever nonlinear differential equations, you're in trouble. So if we have linear spaces here, so we just have Rn, Rm for the actions and states. I'll do it around for the states and actions. I have a disturbance space too called theta. Then I have a linear state transition equation. So this is just like that equation there can express something that looks just like this right here that I already have in a box, right? This is just a special case that's linear. And I explicitly model the disturbance of some parameter here so that I can write an equation. I could have written that as, I'm going to get some distribution over xk's given xk and uk, because I'm not given this. This is a disturbance that's, let's say, is chosen by nature. Right. So that's how it looks. Here's a special example. Doesn't make any. These are just matrices here with constant values, real values, constants. And then I have an observation space, which again is R, let's say I, and I have a distribution of disturbances over a space Rj. I should have the set, let's say, not distribution, but I have the set of disturbances Rj. So then I end up with this equation here. All right? And now I assume that the theta and psi are zero mean Gaussians with some covariance matrices that have been given, right? So that means the system I've defined here is linear and Gaussian. Those are the two prettiest things, right? Gaussian distributions are the simplest to work with in probability theory, and because the second moment approximations of them are themselves, right? So you don't get more moments. They're very, very nice to calculate with in probability theory, and for control theory, linear systems are perfect for calculation as well. So it's a perfect union of these things. It turns out in that case, what happens if I take linear combinations of Gaussians? Anybody remember that from probability theory? I get more Gaussians, right? So I have an algebraic closure on the space of Gaussians. So what's happening to the information space for the Kalman filter is going to be that instead of having all possible probability distributions over the state space, everything's Gaussian. So what would be the dimension? Suppose I start with a three-dimensional configuration space. What is the dimension of the space of all probability distributions? I don't know, infinite in general, I guess, right? If I just specify it's a function space, so maybe an infinite dimensional space. However, if I know that I have Gaussians, then it's only whatever I need to specify the mean and covariance, right? It's only the parameters I need for that. That's enough to specify the Gaussian. So it becomes finite dimensional and sometimes not very high dimensional. That's quite nice. So there's a bunch of stuff that happens. I don't care to derive this stuff. I don't like linear algebra too much. But you can go through and derive all these things. There's a matrix inverse in here somewhere, so it leads to some numerical problems. But there's ways to fix that and such. But there's some equations here. And I just want to say that by the time you're done with them, you end up with an expression like this. The next mean and covariance is a function of, so here's my filter notation, the previous mean and covariance and the two new pieces of information. So it's exactly the Bayesian update, but it just happens to work out because you're trapped in Gaussian land, let's say. You stay in Gaussians forever. Every time you get a new action or a sensor reading, you stay Gaussian, so you have a closure here. It's quite nice, and it doesn't model everybody's problem, but when it does happen, it's a beautiful collapsing of the information space. And that's the kind of thing I want to see in many, many more kinds of problems in robotics, a kind of collapsing of the information space. But for our problems, it's not going to be linear, it's not going to be Gaussian, it's going to be something else. But I still like this idea that the information space for this problem collapsed down very nicely. It could have been an infinite dimensional function space of all probability density functions, but instead, it's only the space of Gaussians. Do you believe that's a smaller space, right? All probability density functions are all Gaussians, right? All Gaussians is much smaller, just mean and covariance is all you need. So that's a beautiful idea behind the common filter. It's easy to get lost in all of this sometimes. See, what does that say? The new mean is a function of, hey, is there a previous mean in there somewhere? Let's see. Thank you, there it is. Yeah, see, it's hard to even find it in there, there's so much algebra. I don't really care. All it does, I mean, there's a covariance update, and it's all the right things you need are embedded in there as well. But, it's as simple as an expression like this. In fact, people love this thing so much they made what's called the extended common filter, which just keeps approximating the result as Gaussians, even when it's not. Sort of okay to do that because then you're taking second-order moment approximations of distributions or densities at every step. And, it's fine. In most applications where people use it, it's not theoretically guaranteed to work for them, but they do it anyway. And people find a lot of use for it. So I just want to point that out. So the common filter fits inside of here. Questions about that? So just, again, appreciate that. Whenever you go back, if you use the common filter, you think about it, appreciate the fact that an infinite dimensional space of density functions has been collapsed with this nice algebraic properties to a finite dimensional space of Gaussians. That's very nice. That doesn't really happen too much. I can't think of any other nice examples like that. That's why this was a big deal. All right, so a little summary of these general filters, and then I want to go into some specific combinatorial filters. So remember that in the non-deterministic case, we had set union and set intersection. Those are the two cases that we had. You get set union when you take into account the action, and you get intersection when you take into account the observation. Then we did the Bayesian version, where you get marginalization when you take into account the action, and you get Bayes' rule whenever you take into account the observation. So in both of these involve, let's say, in general, if you do it in the most general form, right? Say we have some big state space that we like in robotics. It could include the configuration of the robot. It could include possible polygons that it might be inside of, things like that. Then, if we just want to compute these filters that I gave you, we're in a lot of trouble, right? Because they're going to be, can you understand that, right? To do these operations up here is going to be very expensive in general, maybe quite impossible, so to do in any reasonable amount of time. So, what are your choices? One, get a bigger computer, right? You probably want to find one big enough for what we want. You could resort to sampling-based kind of techniques. You could compute approximations, like these extended common filter, as I said. But what I want to do is use the bottom one here. I want to say, let's look at the task. Look at what you're trying to solve, actually. Maybe I want to cover the floor with a robot. Make sure I sweep everything. Maybe I'm playing a game of hide and seek. Maybe I lost something and I want the robot to search for it. What's the task? Those are examples of tasks. Based on the task and the models that I have, the type of sensors and such, I want to try to reduce the overall complexity of the filter. That's how I want to try to think here, rather than doing these other steps. These other steps are probably done, I would say, by people in robotics 98% of the time. I would like this 2% to be 98. I don't know. I would like it to be bigger anyway. I think that people should think about this a lot, and you can write lots of interesting papers if you have something nice to say about how for your particular problem, there's some special structure that lets you use simpler sensors and simpler filters and more efficient computation. That's the idea. Does that make sense? All right, so that's hopefully good. All right, so let me talk about some combinatorial filters now. All right, so I want to reduce filter complexity, and I'm going to provide some examples of that here. I have one called obstacles and beams, one called shadow information spaces, which generalize pursuit evasion, and another one called gap navigation trees, which use that gap sensor that I introduced a couple of days ago. So I'm actually using stuff that I defined, which is good. All right. And you can do many more, and I have other ones that I'm not presenting, but I have to be reasonable here, so I don't want to go on forever. But I'll present these, and that might probably finish me for today. So obstacles and beams. Consider a problem like this. I think this is very nice. So suppose there's a body. Again, it could be a robot or a human. And it goes moving around along this blue path. And at each one of these red line segments, we have a detection beam. Remember detection beams? They always detect that the body went through. These are very thin detection beams. I would usually draw them as a big blob. So these are detection regions that are called beams. This means they're look like line segments. Here's what the history information state looks like. I didn't write it with the parentheses and commas here. I just made it, I don't know, look like a string, I guess. It's still a sequence, so just different notation. And so if I give you this string, can I figure out what state trajectories are possible? Right? And so that looks like one of our non-deterministic filtering problems, right? And let's say that the model I have of how this moves is when I don't detect it, right? So how does this work? So my stages here don't correspond to particular times, right? A stage occurs when? That's right, when you hit a beam, right? So when the body hits a beam, that's the next stage. So I don't know how much time is passing between that. I don't care. And I will make a very simple motion model. So my motion model, instead of making something really complicated, I talked about this kind of thing. I have f of x, k, uk. Okay, this problem is so simple that it doesn't have a uk. So it's just f of xk. And all I want to say about this is that what looks like an invader, if you like, can move arbitrarily fast. I will say that. But it cannot move infinitely fast. So it cannot just jump to some other place. But I do not have a speed bound for it. So I'm going to use that same kind of model that most or all of you are familiar with that's used in these visibility-based pursuit evasion problems. The evader can move arbitrarily fast. That's the model I want here. All right, so I want to make a filter that helps me describe what state trajectories are possible. Or it might describe what is the possible current state. In fact, let me jump back just a little bit here. When we did general temporal filters, I said there were two questions, right? What is a set of possible state trajectories? And I said, what is a set of possible current states? Those are the two things I want to look at here. So same kind of thing. And I should say that, remember, this is a virtual sensor model. So you might have some actual beams like this. We made some beams in our laboratory. It was really easy. You can take a cheap laser pointer, right, that people other than me like to use for presentations, right? And then you can point it at a photodiode, right? Or a photoresistor if you have a little more, but a photodiode, something simple like that. And then if somebody passes in between the beam and the photodiode, then you detect, right? Very simple. So for very low cost, that only costs a few dollars, you can get a beam. However, you can get beams from stuff like this. Suppose you're out moving around in an environment where there are some landmarks. And maybe I have a camera, and I see whenever one landmark passes in front of another. Right? Imagine you're walking around in the city here, and you have some really high towers, and you see them off in the distance. Whenever I see one tower pass in front of another, I can just call that a beam. The event of that happening is like a beam. If that's the case, I would get a picture like this. Is that right? Here's another example. I could maybe say that I have a compass, and I keep track of whenever a tower is directly to the south of me. That looks like beams that point north. So with many different kinds of sensing scenarios, you can get these obstacles and beams. So I just want to say that this isn't only an example, but I think it's a very important family of virtual sensors. And it fits inside of detection sensors, so it's a subclass already, right? But a very important family because it has many different physical realizations. Right, so let's think about this very carefully. So let's look at what we call regions. I assume you can probably compute cell decompositions for something like this, right? To nicely compute regions and which regions are adjacent and that sort of thing. Use half-edge data structures or whatever you like. And we have a collection of regions here, R1, R2, R3. And by region I mean a maximal subset of the environment in which a body can move without being detected, right? These regions can be kind of strange and complicated here, right? Because you can move on either side here without being detected, so that's fine. So now I'm going to make a very simple region filter. And I'm going to make some assumptions. I'm going to say whenever I make a beam, it should connect from the boundary of E to the boundary of B. I don't want a beam that's just kind of in the middle somewhere. And if it turns out that, I'll even allow unbounded environments here if you want. So if that's the case, then the beam needs to go off to infinity. There's no way to get around the beam. Because I had some examples that go off to infinity in this picture, right? These look like they're going off to infinity, so that's fine. You can't just have the beam stop here and then you can go around it. So I want to make that assumption. And I will assume for a while that each beam is uniquely labeled, so fully distinguishable beams. There's a reason to not do that in a little bit, as I'll show. And then I want to also assume for a bit that I do not allow beams to intersect. So I have disjoint beams. And then let's also suppose that I know the initial region that the body is in. Here's a very simple filter. I say, given the previous region and the new sensor update, I calculate the next region. If I have this observation in the previous region, guess what? There's only one possibility each time. Right? So, imagine if I go through here, it's very simple. If I'm in R2 and I observe B, where am I at? R1. If I observe A, R1. Right? So now there's one assumption I'm making here, and that is that this body cannot go up to the beam and then come back. Okay, there it doesn't make any difference, but it cannot go up to B and then come back without entering R1. So that's a kind of a special case. I can go general position, blah, 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 and then it all goes away, right? So it's like a general position. So I'm not going to allow that case. So if that's the case, that's a ridiculously simple filter, right? It's almost embarrassing for me to present it, right? It's very simple, right? However, it is calculating exactly these sets, right? That's doing exactly these calculations in a clean, exactly this. Oh, no, not that one. It's doing the non-deterministic one. So that's calculating exactly xk. Oh, what did I call it here? I had, a to k. I don't have u's here. There's no actions for this, okay? So be careful, there's no action. So that's okay. My a to k here is just equal to y1, yk. And there's no u's for this problem. It's too simple. So I actually did an example here, very simple, of calculating this. Right? It could have been a horrible problem, but I chose a motion model that says that the body moves arbitrarily fast, and I chose a nice model of beams that look very much like the kind of model a computational geometer might like to make. And then, no big surprise, the calculations here end up being very simple. I don't end up resorting to very complicated particle filters, and I don't have to make probabilistic models about how this body might move, right? I could have done all sorts of things I could have done to make this complicated. But with very, very simple filter here, I just figure out the regions. Is that okay? All right, so then, that's how the filter looks. Just gives me the next region. And here's this phi again, so same idea. Just based on the previous region and the observation, I get the next region. Let's make it a little bit fancier. So I could say that beams may or may not be distinguishable. Now that might seem ridiculous, right? If I go put a bunch of sensor beams in an environment, don't I know which one is which? Well, I can get different interesting cases. For example, if I go back to this case here, what if I don't know which landmark is closer when they pass? If I don't know which landmark is closer, very simple. There's a lot of, the thing you have to keep track of is we're making virtual sensor models, so they can have many different physical implementations. So if I have two landmarks, so I told you that you get sensor beams like this, right? That should not be curving. I get sensor beams like this. But if I don't know which one is closer, so if I pass this way or I pass this way, then maybe I just label them both A, because I cannot tell. Right? So I don't know. I know I passed over those beams, but I have essentially two beams, and I'm not sure which one I crossed. So this kind of thing can certainly happen. So let's allow the beams to be, they may or may not be distinguishable. They also may or may not be disjoint, so we will also allow beams that, that intersect. So I may put other beams in here. Perfectly fine, we allow intersections. Also, I'm going to introduce a new concept. I may give beams with direction. So in other words, when you move through the beam will tell which way the body went. Left to right or right to left. It's actually very easy to take two undirected beams and simulate a directed beam. So I may write something like this, let's say. I may make a beam and say it's directed. So this might be the direction of the beam. Obstacle. I have to say they go from boundary to boundary. So this might be the beam. So I can tell the difference. If I go, for example, in this direction, I observe A. If I go in this direction, I observe something else. Maybe like A inverse or A leads A prime or something. You know, it's the opposite direction. So I can do that. And if I want to simulate something like that, I guess I can do it like this. I can just have two beams. And I call, they're really close together, I mean. And I call this one A1 and I call this one A2, right? And now when the body goes through, assuming it doesn't go in the middle and come back. Right? So if these are imagine A1 and A2 are very close together. So if I get A1, A2, that's equivalent to A, right? But if I get A2, A1, that's equivalent to going through A backwards. So just something to think about. So it's nice to think about directed beams. They're very closely related. So this is kind of my favorite model out of these virtual sensor models. I found a lot of use out of it. And I think I will be showing some things where we got quite a bit of use out of it on the very last day of this course. So I'll show you some newer stuff that we did with these. All right, so now we have these complicated beams, like I said. Here's an example. There's 8 regions. And, you know, there's a B here and a B over here, stuff like that. Right? I still wasn't too imaginative. I put everything at horizontal or vertical polygons. I'll leave it to the combination geometers to make more horrible looking examples. So you can make really complicated ones, doesn't matter too much. So we can make a very simple filter. I don't think there's any interesting complexity questions here, really. It's quite simple. Just make a multi-graph that corresponds directly to the regions, right? It's a kind of dual graph, if you like, to the region-based representation, or the dual to the cell decomposition, if you like, where every vertex is a region. And then I put edges in here. Yeah, I use A prime for the reverse direction. I put edges in my graph, including self-loops. They're directed edges. If it's possible to go from one region to the other by crossing a beam, and then I put the label of that beam on the edge. That's all. So I just make a graph that keeps track of all the possible transitions. And then it's very, very simple. I just keep track of the set of possible regions for each observation. So all this is doing a very simple calculation that just is doing essentially the forward projection on the space of regions. It's saying, hey, if I started in these possible regions and I got this observation, what's the next set of possible regions? Still ridiculously simple, right? Nothing complicated here. Is that okay? It should be kind of simple, right? So if I go back here, just imagine, maybe initially I could be in any region, but then after I observe A, where might I be? Well, I could be in R1. Where else? R5 and R2. And R4 and R3, is that right? Yeah, for observing A. I think that's all. And then if I observe C, where might I be? Well, if I observe C, I could not have been in R1, right? So that gets eliminated. Yeah, I think so. So I think you're getting it, right? So you can eyeball this. It's not too hard to do this computation. Much, much simpler than calculating some complicated Bayesian filter placement. If I have more bodies, I can do something not very inspiring, but I can just take the Cartesian product of these regions, of the region sets, and then do calculations over the power set of that. So for example, if I have 3 regions and 2 bodies moving around, then I have 9 combinations, right, of 1 region for each body. And then I can calculate the set of possibilities for that. In other words, what set of pairs is possible. And then again, use this graph that I made to very simply deduce what sets are possible in here. I guess you can see a problem in this, right? It becomes horribly exponential in the number of bodies. Before too long, you'll end up with a mess. Nevertheless, that's how you do it. Just take a big Cartesian product and continue to do the transitions. I'm not going to go over too much, but just in a straightforward way, you can use the multigraph to calculate this over for multiple bodies. However, there's an interesting question here, right? So computing this non-deterministic filter seems to get complicated based on the number of bodies. However, there are some tasks where it still might get simpler. And let me show you an example. So this leads to a very great kind of open family of questions, which is, for what tasks is the corresponding non-deterministic filter of low complexity? That's what I want to know. I will show you one that we have that's very pretty, I think. It works out very nicely. We did this with Benjamin Tovar and Fred Cohen. It's running off the bottom a bit there, but it doesn't matter. So here's the idea. I have exactly this problem again. And here's the question I ask. Are the 2 bodies in a room or region together? In other words, are they together here? Are they together here? Or are they together here? If one of those 3 cases is true, the answer is yes. Otherwise, the answer is no. Suppose my task is just to determine that. I don't want them together. I don't want them talking to each other. I don't want them together in the same room, right? You can make lots of interesting examples from everyday life, but I won't do that. We want to keep them apart. All right, so I just want a filter that does that. Do I have to reason about this? Do I have to look at all 90 cases here? And then I need the power set of that, right? How many cases is that? 500 and, what's 2 to the 9th? 512? There's one case that's missing, which in that case, if we use non-deterministic uncertainty, because the empty set's not needed, so it turns out that this will blow up to make 511 cases. So we can make this gigantic combinatorial filter, well, kind of gigantic, not for computers these days, but back in 1968 it would have been a mess, where we have 511 states, and we could do it that way, but we found a way to answer this question with only 4 states instead of 511. Right? Here it is. So this means they're together. They could be together like this, or together like that. And then, well, even says 511, very good. Then, if you observe A, what happens? If they're together and you observe A, then you know they are not together, correct? And you know that A separates them. So that's this state. They could be like this. It could be blue here and red here. Or it could be red here and blue here, right? But that's what you know. It's that or that. In the diagram, you transition up. If you get another A, you go back down. Now, they could have gone like this. They could have started here, one goes up and then comes back down. Or they could have one go up and the other goes up. They could have changed rooms, but I don't care. Because in terms of my information, states that I need to keep track of, that's a self-loop. Because I don't care. I don't care what room they're in. I only care whether or not they're together. I don't want them together. Right? All right. So that goes up and down. And the same thing happens for B, and the same thing happens for C. Now let's look at these outer edges. If they're separated by A, and then I observe B, that means the one up here jumped down like that, right? So that means they're separated by C. So I'm up here, I observe B, I jump down here, they're separated. This is different, D for different. Different rooms, but they're separated by C. How's that? Very nice, right? So that's what I would call a 2-bit filter. You need roughly 2 flip-flops, right? You need 4 bits, no, sorry, 4 states or 2 bits to represent this. And it's very nice. So that has the same filter structure, see, right? Doesn't it? It's just like our filters. It's doing these calculations of sets of possible states, but it's actually made a kind of approximation to them. And it's just enough, it's a very coarse approximation to the set of possible states, but it's one that's sufficient for answering this question, are they in the same room together? Isn't that very nice? So I appeal to you, go find some other questions you can ask that take these gigantic Cartesian product, kind of horrible information spaces and collapses them down nicely. Same feeling like in the Kalman filter. You collapse the big space down nicely. Instead of being linear Gaussian, we had a nice question. And then it leads to a very simple structure. Yes?
Can you explain the example?
Uh-huh. The graph is the filter. Let's explain the graph like this. Let's construct the graph, right? So, and let's suppose I tell you that initially they're together. Actually, the initial information is very important here. You just initially need to know where you are on this graph. If you don't, you have a problem. So suppose initially I know they're together. Is it clear what together means? Okay, right? It means 2 here, or 2 here. If I observe A, what does it mean in the picture? 1 here and 1 here, right? But I don't know which one is above or below. I don't care. Because the question doesn't care. As far as the question, and that's one thing to pay attention to. The question does not distinguish between red or blue. Right? It doesn't say blue is to the left of red or something like that. It doesn't say that. It says, are they together? So since it doesn't distinguish between them, it doesn't matter. So that means if that happens, if I observe A, I write it like this, I'm making a representation of this function. Okay? Where these I values, ik and ik minus 1, are taken from this set. So I'm just depicting this function with a pretty automaton picture, that's all. So in other words, this is the current state and this is the observation, right? So this, the yk here would be A, and then I go up here to this. This now represents that they're separated by A. Is that okay? And now if I get another A, I come back. Because they might be together, they should be together again. And so by symmetry, right? Symmetry, the same thing's going to happen. There's nothing special here about the other one. This happens. So we only have a little bit left, right? We just have to figure out if they're different and they're separated by A, then if I observe B, what happens, right? So that means one of them that's up here went down here, right? And the other one had to be over here then. So that means that you have them on either side of C. So they're separated by C. So I go down like this. And then I just, by symmetry, is that case okay? And then by symmetry, I just add all the rest. So the same thing happens all around here. Okay. So isn't that pretty? A very, very simple filter that answers this question. There's no actions here.
No, but I'm asking, is it possible to draw the duality between the graph that we're making for sensing?
Yeah. Well, so if I start putting actions on this, and actually I'm going to get to that in the last talk that I give at the end of the course. I might write a plan or a policy that's a function from an information space to action. That's how we write a plan in a general setting. A function like that. That I is this I, only for this problem. So the interesting question is, what kind of plans can I make? I will show you a very simple example where I can make a very simple system where the plan can keep these two robots separated. Because that's what this is designed for, it looks like. Or I can keep them together, is another way I do it. Because that's all I can distinguish between here. So if my task involves keeping them apart or together, I can make simple plans like this and try to help enforce that. And do a little bit more on top of that, which I'll show you. Is that okay?
Yeah, that's the thing that comes with the work that Frank is doing. That his sensor is actually not a sensor basically, because it doesn't sense anything. It just either push. And then by actions,
Yeah, that's right. That's right. That work, and Frank should probably talk about it more than me, but that work benefits a lot by the power of funneling, and that even though you have no sensor feedback, when you apply the action, the set of possible states is reducing substantially. So in a lot of that work, there's a non-deterministic filter that's being implied. So you go from set to set to set to set, but by some chain of actions, it converges to knowing the state, which is magical and wonderful. It doesn't happen very often like that. It's very nice when it happens. Very odd kind of thing. That does not correspond at all to our intuition about a mobile robot that's just going out and exploring. But for some of these very particular kinds of cases, and a lot of that's due to mechanical compliance. So the mechanical system itself is relying on things like you could use gravity, you could use friction, sliding, and things like that, and that's what's often relied on to cause these kind of funnels, let's say. I don't see funnels here necessarily. This one's still remaining at the level of regions to regions to regions. So in Frank's goal, in Frank's problem, the goal was to estimate the state, which is the orientation of the part, for example, right? Here, the goal never involves that, so we never estimate that. We never make models of where those guys are. We never make models of probabilistic transition laws. I don't have to do 100,000 experiments watching how these guys move to make a filter. I just set up my beams and I'm done. Because I avoided all of that stuff because the task doesn't care. And you might ask yourself, okay, maybe the task is useless. Fine. You know, for some other tasks it's more useful for you, then try to ask the question. I encourage people, try to ask the question, for my task, can I get away with a smaller filter that does not need to reconstruct the state? Frank's task is to reconstruct the state, which is a perfectly fine task and is needed for, let's say, a manipulator is going to go and pick up the part next or put them all in a box and pack them, things like that. Then that was the goal, in which case you did what you needed to do. But still with very little sensing, or no sensing in some sense, and that's very nice. Is that okay? So that's kind of how I see those two related. Was that fair enough? Yeah. Okay. I don't think we're competing. I think we're quite compatible, right? All right. Next one is this thing. Oh, are there any more questions about this stuff? The next thing I want to do is I want to make a family of filters that generalizes pursuit evasion. And in the process, you can replace the filter that's essentially inside of all of your pursuit evasion formulations with this one, and that will take, it sort of like gives you a whole collection of open problems for free. You know, some open problems are better than others. It's easy to make impossible open problems, right? So, and trivial ones don't last very long. So, you know, are there some good ones that are in between? I don't know, but I will show you how to get some open problems from this thing we call shadow information spaces. The shadows are just the places that you can't see, which I will show you in just a bit here. So, here's the idea. Now, because I'm at the level of filters, I don't even have to worry about whether I have one or more cameras or visibility sensors. I don't have to worry about whether it's a simple polygon or not. I'm going to formulate it in such a general way, and then the particular implementations will worry about these things. For the particular algorithm or complexity, it will depend, but the general formulation doesn't really care. So I'll make it look kind of general. Here's kind of a crazy problem. There's, let's say, 3 white robots moving around, and you see they have omnidirectional visibility. And instead of evaders, we have a bunch of colorful targets moving around. They have different colors, and the reason why I gave colors to them is so that we can make them any level of distinguishability. They could be all red, or each one could be a unique color. Here's an example that's in between. So I cannot distinguish the reds from each other, but I can distinguish a red from a blue. So I can do anything with this model, just by any sort of level of distinguishability. And what I want to do, oh, and notice the bodies can be inside now, right? In the pursuit evasion formulations that most of you are familiar with, you never actually reason about the evader during execution, right? All you do is develop a kind of open loop strategy so that when you're done, you're guaranteed that you will have seen the evader, right? Or it's kind of like a proof that there was no evader. It's like another way to look at it, like a verification that there was no evader. Now imagine we really put the evader in, and we keep track of it somehow. But instead of one evader, there's a bunch of colorful evaders. Right? And the game doesn't end when they're detected. No way. So it's just going to keep going. If you want to make the game end at any time, go right ahead. If you'd like the game to end when you see 3 red invaders, that's your problem. Go ahead. But I'll just let it keep going here. And I just want to talk about a family of filters we can make for this problem. Does that seem fun? If I were really clever, I would have a movie here. I need to have these white robots moving around with all the visibility, and then you get the idea. So this should be, imagine being animated. These white ones here are moving, as are everything else, all the colorful ones as well. All right. So I have the detection region, just like we talked about. The complement of the detection region is called the shadow region. One interesting thing about the shadow region is that it has a finite number of connected components. And finite and not necessarily one, right? So it divides into pieces. Each one of those pieces is what we might call a hiding place if we were playing pursuit evasion, right? So the shadow depends on the configuration. In this case, the configuration is just a position, but we can make it more complicated if you want. I don't care. It really doesn't matter. Any kind of detection regions you want to make that depend on configuration are just fine with me. In fact, you could even have a couple of stationary cameras and a robot moving. The whole thing would just be V of Q up there. Is that okay? And then the complement is S of Q, the shadow of Q. The shadow at Q. All right. Well, we saw this, and for those of you who were at yesterday afternoon, late afternoon session, I think we saw appear, disappear, split, and merge in another context. So I like those terms. We have several different things that happen, which, if you're familiar with the visibility works, I'll show pictures of it in a minute. That if you're familiar with the visibility-based pursuit evasion works, you'll know something about this. So we have disappear. So as a shadow, so in this case, a shadow component goes away. And what happens is it eliminates a hiding place for the bodies. So I'm really thinking about these bodies now. I'm not just trying to eliminate them in the analysis like we do for visibility-based pursuit evasion. Up here, a shadow component appears, and it introduces a new hiding place for the bodies. Let's say they hide outside of the field of view. Split, a shadow component splits by component. I just mean connected component in the usual sense. A shadow component splits into multiple shadow components. And merge, multiple shadow components merge into one. And if you're worried about some special cases, ignore them. All right, so just for this. All right. So here's up here and disappear, right? If I move my robot up and I have just an omnidirectional sensor. Now, this stuff I'm talking about will apply to any kind of detection region. It doesn't really matter. All that matters is the components of the shadow region. So that's all that matters. If you can get those components, all of the stuff I talk about works. If you can't get those, then okay, the stuff I'm talking about does not work, and that's it. But there's many different, it could be 3D visibility, complicated stuff. It theoretically is possible, but practically impossible. But what I'm saying still holds for that. All right. So if I go up, the brown area disappears, correct? If I go down, it appears again. So that's appear, disappear. That's it. That's an inflection, right? That we talk about sometimes. Here's a bitangent that we talk about sometimes. If I'm in that case up there, probably shouldn't have drawn it in both places in both pictures, but if I'm up there, then if the robot's in the top part, I see 2 shadow components, but when it comes down, I get one big one, right? Or the other direction, I get one big one on the bottom, and when it goes up, I get 2. Be careful about the structure of the environment, right? When I go up and down on this one, does anything happen? I still have the same shadow component, right? So I do imply that in order to know the shadow components, you have to know something about the topology of your environment. However you get that information. Maybe it's assumed, maybe you assume it's a simple polygon, so you don't have that. Or maybe it's like this, in which case you need to know something about the environment. You know there's a hole there, fine. I can even have this stuff working in an unknown environment if you can still infer the topology. Maybe you just know enough about the topology to answer the question about what the shadow components are topologically, and that's all. That's okay. You don't need exact geometric representation for this either. All right. So what information do we have? Let's think about it. So here's a set of shadows, S sub k, let's say, at some stage k. And we're moving around, I guess there's really like a continuum of stages here, but I will say there's a stage K changes to K plus 1 after either one of these 4 events occurs. Right? So one of these 4 events occurs, we're at the next stage. So what can happen after these events? Well, disappear means a shadow component gets removed, right? Appear means some shadow component gets added to the collection. Split introduces some relation on 3 shadow components, meaning that this one split into these 2. General position assumption. We don't do a triple split, but of course that can happen in here. Merge. We have a merge relation that means that S and S prime merge to form S double prime. So I just want to say that's exactly how these things are together. And one of the most complicated things to reason about is what happens for split and merge. So this is how I imagine the operation of this filter. I have some components up there that I just drew abstractly as nodes, and I get a flow in the downward direction, stage by stage by stage. So here's a disappear occurring, right? So S4 is gone, it's dead now, so it never appears again. That's another one, it's S9, so it never appears again. Here S7 appears all of a sudden, it starts a thread, if you like. S3 splits into S8 and S9, so that's just this blue part here, that's a split. And here's a merge. S9 and S5 merge into S10. So that goes here to make a new one, right? S3 died, and S10 was born, right? So just something to pay attention to. Now let's make filters. This you probably are familiar with if you're familiar with the pursuit of Asian works. In fact, you got some background on this, even if you don't have prior background. There were some lectures on this before we started the course, right? So there was some pursuit of Asian in that. Is that right? None of that? Okay, just visibility. Okay. Oh, that's fine. All right. So, all right. So here's the idea. So here's pursuit of Asian. We want to know: is there an evader in S of Q? So this is exactly the basis of a lot of methods, including the ones we developed for pursuit of Asian algorithms, which is for each one of the shadow components, I'm going to keep a bit, 0 or 1. 0 means there is definitely not a body, or evader if you want, in S1. And 1 means that there might be a body, I'm not sure. It doesn't mean there's definitely a body. Actually, you can make a third label and you can put, and you can reason about that. Okay? So that's what this means. Does that make sense? If I'm playing a game of hide and seek, there's all these components that I can't see right now, and I'm wondering, I know there's nobody there, but there might be somebody over there, right? That's how I think. So just a single bit is all that's needed. So to make the filter, here's what we did. We just make these nice update rules going from SK to SK plus 1. So if you disappear, nothing happens. I have to update the labels that I assign, right? That B function is back here. This is my B function, it just makes a label, right? Takes every shadow and sticks a label on it. So, we have these update rules, and in the case of disappear, there's nothing to update. Some shadow component went away. When we get to the appear case, what happens? When a shadow component appears all of a sudden, like, well, imagine I was really low to the ground, and I go looking around like this, I know when I come back, a shadow component appears that corresponds to that, and there's nobody there. Because I'm watching everything else, right? Nobody can sneak there. Frank can't jump back there and watch it. No, not going to happen. All right. So, so that's why it gets a label of 0, because remember, 0 means there's definitely nobody there. The split case, what happens in split? All that says for splitting is you take the label that was on the shadow and you propagate it to the pieces that it splits into. So if I thought there was somebody hiding in some region, and then I noticed it split into 2 regions, there might be somebody hiding in either one. Merge. Merge is the interesting case. The only way we can get a 0 label on merge is if the 2 pieces that form the merge also have 0 labels. If there was nobody hiding in either one of these areas over here, then when we merge, there's still nobody hiding. But if there might have been somebody hiding in either one of those, then when we merge, we get a 1. So it looks like logical OR, if you want to imagine logic on this, with 0, 1. 1 meaning true and 0 meaning false, and it looks like logical or, and that's all. And the, number 2? Well, because it appears. So, I don't know if I can get a good example. I can't, these things aren't big enough here, but you know, if I go back like this, all of a sudden a shadow is appearing. There's a shadow that appears like this, and there's nobody back here because I was just looking at it.
No, that's the assumption that if you, there's no shadow, you're sure there's no one there. But in the original problem that you showed, there were some agents in the view.
Oh, very good point. Yeah, very good point. So for the problem of pursuit evasion here, yeah, that's right, that's right. So the problem of pursuit evasion, yeah, that's interesting. Let me see if I can make some kind of weirdness here accidentally. You're right. So in the original problem, I'm allowing these guys to be in the field of view. That's right. And here, when I'm making, I think I'm implying some understanding about the pursuit evasion problem, which is unfortunate because it causes confusion here. So that's a very good point. I'm not taking into account that. The game ends if there's an evader detected, and then the whole thing's done for the pursuit evasion problem. So as soon as that happens, you're done. Let's assume it did not happen, and you're trying to go around and find the evader. And just for fun, let's suppose there is no evader, but let's suppose you have to go and verify that there's not one. You're the security guard of Undercover Technical University, and you have to go around and make sure that there's no foreign professors running around the campus. Right? You have to clear them out. So I was having a little fun. They were extra secure this morning for letting us in, but probably because of the election, right? So, all right, very good. Or because it's Friday, you know, not very many people here, so it's understandable. All right, I'm gonna say a little bit quickly about this, and then I'll go back over it next time. But because you're probably getting a little bit tired, but we can generalize this further by making something called a count bounding filter. The idea is that I take every one of my shadow components and I map it to the natural numbers, but I also include 0 and infinity. So numbers, any positive integers, or 0 or infinity. And there's a lower bound and an upper bound. And what that's going to mean is how many bodies are there? Right? I want to give, for each one of the shadow components, an upper and lower bound of how many bodies are there. If the bodies are in my field of view, I know how many there are there. But I want to keep track of how many are in the places I cannot see right now. Upper and lower bounds. The upper and lower bounds collapse to 0 and 1 for the previous example of pursuit evasion. But here I want to make it more general. So I want to say, I want to keep this upper and lower bound and reason of it as I go. If I have no information, then I will say it's 0 to infinity. If I know the value, I will just say the lower bound and the upper bound are the same. There's 5 in that shadow component. So that's the idea. So now, if we want to make a filter for that, we just have these updating rules, which look just like the updating rules for pursuit evasion, which is this one. This one was very simple. This one's a little more complicated. Let me talk about merge. So if we have merge, what happens? So if the lower bound for two shadow components were this and this, then when I merge, I'm just going to add them together, right? Upper bound, this and this, when I merge, I add them together. Okay? So that's quite simple. The appearance case, I'll just assume that whenever a shadow appears, there's nobody there. So it appears with upper and lower bound of 0. Disappear again has nothing to update. All that leaves is the split case, which does what? So if we split, what is all that saying? Let's see. What's that? UK is a problem. Thank you. Yeah, that should be L. Wait, no, what should it be? Why is there a UK there?
UK crossword.
Oh, sorry, upper bound. Yeah, I'm sorry, upper bound. I don't have to be. This one should be. Okay, is that?
No.
We're on split?
First. Yes, UK crossword is this one.
UK plus 1. Okay, yes, third one.
Delta plus 1 and delta plus 1, the other one
It's you.
should be
It's you. No, but it's for S
yeah, let's finish on that, and we'll figure out what it should be next time. How's that? Okay. I'll come in with, or you can solve it for me if you want. What should it be? Here's the homework question. What should the rule be for splitting if I have upper and lower bounds? Yes?
Better to act something here because the invaders can move and maybe move from
Good.
part to
Good, good, very good. Yeah, that's right. There's two types of events. These are the shadow events, all these four events. And there's another kind of event, which I've neglected here, which we call a field of view event, which is when the bodies come in and out of your field of view. And when that happens, you update these counts also. Because whatever shadow they came out of, you lower the bound, right? And then, like, if you have an upper bound and they came out of it, you can lower that. And then when you and then if they go into a shadow, you increase, right? Right, so you have simple updates for that too. I neglected to say that. Thank you.